So, good morning, good afternoon, and good evening, depending on where you are. Welcome to the second keynote speech at SPMF 2020. It's my great pleasure to introduce Dr. Nikolai Bjorner. He received his master's and PhD degrees in computer science from Stanford University. And now he is a principal researcher at Microsoft Research, Redmond, US, working in the area of automated theorem proving and network verification. His current main line of work is around the state-of-the-art theorem prover Z3, which is used as a foundation of several software engineering tools. Z3 received the 2015 ACM SIGPlan Software System Award, the most influential tool paper in the first 20 years of TACAS in 2014, the 2017 Skolin Award for the 2007 paper on efficient e-matching for SMT solvers, the 2018 ETAPS Test of Time Award for the 2008 paper on Z3, an efficient SMT solver, and the Herbrand Award at CAD 2019 in recognition of numerous and important contributions to SMT solving. Hopefully, I have mentioned all awards and didn't forget anyone. And today, in his lecture, kindly supported by Formal Methods Europe, he will talk about the universe of Z3 theory solvers. Nikolai, it's a great honor to have you here. Thank you for joining us.
Well, the privilege and honor is all mine. So thank you very much to the organizers for inviting me. I really look forward to visit Brazil and importantly interact with attendees of the conference and university in the universities. It's an important part of our work to have good interactions and feedback. Now, unfortunately, that's not going to happen in the personal way. I hope to still get some interactions and hopefully give some ideas of what's going on in the solving world through this talk. So the scope of this talk is can be seen in the sense of what Z3 system is, and Z3 is available on GitHub. Here's the source directory, and inside the source directory, there's another directory where the SMT core solvers reside. And schematically, it looks like this. Z3 takes formulas, whether they are encoded in a programming language or in a SMT-lib file in a format, in textual format. And then you can invoke various tactics or solvers to check satisfiability or even optimize objective functions. And one of the solvers, the main solver actually, is what we call the SMT core. Now, if we expand on what is the SMT core, you will see that it comprises of a SAT solver and also a so-called equality and uninterpreted functions, the EUF core, that communicates with two satellites for determining quantifier instantiations. And then there's a set of satellite theory solvers that contain specialized algorithms for solving interpreted symbols of formulas. So these solvers really drive what applications can do. And a big recent development have been a new arithmetic solver that we aim to replace our legacy solver with. And other solvers are also in active development. And I will talk about one where users can supply propagators. And overall, this talk is very much motivated by what I'm currently up to, which is I think these solving technologies are ripe for a next generation core, and that's very much in the activities of this year. So it's a several months effort in developing a new efficient core for solving. So that motivates why uh, I'm giving this particular talk or focus of the talk. Now, we can see SMT solvers in a context of other uh, similar or related solving technologies. And here I'm schematizing SAT solvers, SMT solvers, mixed integer programming, and constraint satisfaction programming. Problem solvers in some comparison of what technologies they rely on. So SAT solvers are scaled to millions of variables and clauses, and it relies on they rely on breakthroughs that were quite were quite frequent in the 2000s. Let's say there's still several breakthroughs happening. Um, but the big wave came in the 2000s. SAT solving is efficient SAT solving essentially relies around cheap local inferences. So you combine a few clauses, you learn new clauses from a few premises, and then search would accumulate a set of learned clauses very aggressively. So why can we do this? Because you can also garbage collect useless clauses in the process. So, so SAT solving really relies on having this tandem of local inferences and forgetting what was useless. In contrast, mixed integer programming well, had its breakthroughs in the 1960s, but really was harnessed by efficient solvers, CPLEX and then Gurobi in the 1990s, and actually by the same team of people. What distinguishes MIP programming is that it essentially relies on a linear programming core that does global inferences. So when simplex pivots and finds solutions to linear inequalities, it each pivoting step looks at all constraints globally and makes a deduction. And then integer programming then relies on catch and branch and bound. Now CSP programming had its breakthroughs in the 1990s, I would say, and here it relies on global propagators. So one way of characterizing SMT is that it strives to have more expressive powers than either MIP or CSP, as it's essentially can integrate such domains that are supported by those solvers. And then it borrows technologies and ideas from the areas of MIP and CSP. And later on in this talk, I will give two exemplars of the global propagation and global inferences in SMT. So the outline for the rest of the talk is as follows. I'll give some introduction to applications of SMT. Then I'll do a 101 on SMT and SAT solving to clarify what I mean with the integration of theory solvers, and then summarize the theory solvers in a ontology based on some ontology of what they provide. And in this process, I'll give the two examples of the global propagation and global inferences that get integrated. So let's start with some applications of SMT. So here I'm listing 4 categories of users, Microsoft users of SET3. And I'll be describing the blue, green, and purple area a little bit more in the following slides. So let me just mention that the application areas use different features of solvers. So some applications use bit vectors only, others use bit vectors plus arrays. Then other applications use arithmetic and quantifiers. And then in the product configurator that I'm not going to talk about after this slide. So let me just mention that um, it mainly reasons about finite domains, but it's signified in that the query it poses to set3 is not whether something is sad or unsad, but it wants to learn consequences. So if you if you say, as an example, if you are choosing the car to be a Ferrari, the color can only be red. So as a consequence of choosing the car model, your color choices are going to be limited, and you can express such uh, constraints, dependencies using logical formulas. So manufacturers use this tool. Now there are many other tools built around set3 that I cannot go into, but let me just go into a little bit more on some selected tools. So the Project Everest aims to verify cryptographic libraries and parsers, and as used in cryptographic protocols. And the main idea around Project Everest is to take a programming language, a program written in some programming language that has annotations. In the case of Project Everest, the programming language is called F star, and it has refinement types. In the context of the verifying C compiler, which we see here in the figure, it takes a annotated C program with assertions and then compiles it into an intermediate format, which is called Boogie. And Boogie tool can then extract verification conditions, so logical formulas that prove the invariance of pre or post conditions. And those logical formulas are then sent to set3. There are several significant systems around besides Everest and verifying C compiler. So significantly for the Frama-C project from France, the Verifast and Viper projects from Belgium and Switzerland, and so on. So that's one application area. Another important application area is symbolic execution. So recently, the tool called Sage, or known internally as Sage, was actually released as open source. So Sage itself was a start of what was called the Microsoft Security Risk Detection tool that I listed on 2 slides before. The way that symbolic execution works can be illustrated with a small example here. You have a flowchart program that first assigns set to x plus y, and then it takes the hash of x and sees if it's equal to set. Now, if you run the program with arbitrary input values of x and y, the chance that x plus y will be equal to the hash of x is fairly small. So, so if we, for example, run with the program with x and y equals 0, the most likely execution path that gets exercised can be characterized as the following formula. So z equals x plus y, and z is different from the hash of x. So that gives rise to a path condition. And then the symbolic execution can flip a branch condition on a so far explored path to see if it can generate inputs to explore a new path. And in this case, the solver can algebraically solve for set. So given any value of x, it can set y to be the hash of x. And in this way, it can find a new execution path. Um, so network verification, another different topic. We have been deploying it for the past 8 or so years in Azure to help validating and linting configurations. What you see here is a picture, schematic picture of a data center. At the bottom, you have servers, and then you have 3 layers of routers on top of those. And the purpose of those routers is to allow the servers to communicate with each other within the data center, and also allow the servers to communicate outside of the data center. So the so-called north-south traffic goes outside of the data center, so they traverse the red routers at the top to get outside. While if you have 2 servers within the same pod, say within the leftmost green blob, then they can communicate directly just by talking to the blue routers. Otherwise, they may have to communicate with the orange routers. So the purpose of the routers is to establish redundant paths and shortest paths between the servers. And so the shortest path between servers within one green area is just goes to the blue routers, and the shortest paths between 2 different green areas goes between the orange routers. So what we do is we check these properties dynamically on the running database, clouds, and by pulling configurations from each router. And then we check the global reachability properties between routers just by looking at each configuration. We establish the reachability invariance from the architecture of the data centers. So the kind of checks we perform in Azure can be characterized as checking connectivity restrictions. So essentially we check whether firewalls do the right job, whether they restrict traffic that should be restricted, or whether they allow traffic that must be allowed. And then we check forwarding policies as illustrated with a data center example. And I gave the example of the live monitoring, but we can also check before we, so an important use of the formal checking is also to sandbox before deploying big changes to the data centers. And then finally, also at design time. So there are different ways of using this configuration checking. For checking all pairs reachability within a data center, there's in principle a very large number of possible paths. If you have tens of thousands of servers, it could multiply up to billions of pairs of racks and a cubic in that number of routes to check. But we don't check such pairs. What we do check instead is local contracts on each configuration. And then we have global properties around the design of the data center to deduce that it actually will route through the shortest paths and have redundant path redundancy. So this parallelizes and scales. So maybe one takeaway from that is that so every problem domain has characteristics that can be exploited. In the data center case, we could exploit some structural properties to have efficient verification. Now, to check each routing table, our default approach is encoding the routing logic into logic and then check satisfiability properties. So to illustrate how this is done, on the left you see a routing table or parts of a routing table. And what it says is if you have it, it starts with the default route or the zero mask. And then the green routing rule is a non-default route. So it takes IP address prefix, and then if the packet matches that IP packet prefix, if the source destination matches that prefix, then the routing rule says you can go to some number of alternate routes, 4 or 8 routes, for example, what it is in the data center. And these rules get applied in some linear order. So we can encode this linear order as a big if then else statement, as illustrated on the right. And then the prefix match is a range match on bit vectors. So we encode the packet header fields as bit vectors. And similarly, with ACLs, access control lists, we can compile access, whether a packet is allowed or denied, into also a big if then else statement. So what you see here is an illustration of a network ACL written in some low-level Cisco format. And then on the right, you see a logical encoding of the ACLs. Now to something completely different. In the financial technology market, there's some users of symbolic solving. The company Imandra sells a tool that's you could characterize as a marriage between ACL2, so the Boy-Moore theorem proving technologies ideas, and symbolic execution. And then they check financial contracts, and in their ground in the end they compile queries into set3 to check satisfiability. And in this financial technology area, a large number of applications these days is around blockchain verification, of course. Now, something rather different is using symbolic solving for quantum compilers. So this is a little project I was involved with, so I can talk about it here. So the idea here is to perform a register allocation for quantum compilers. And register allocation in the quantum world apparently has to be reversible, meaning every computation that is performed needs to be undone. So that gives rise to, or you can abstract that as a pebbling game question. So on the left, what you see is a graph that has to be with variables that we have to assign registers for. So A, B, C, D, E, and F are variables. And as computation flows from the inputs x1 to x4 to the outputs y1 to y2, we'll have to allocate registers and then deallocate registers to reverse compute the results. And what you see in the middle is a pebbling strategy that will add pebbles to these registers and then unpebble them. And that's shown again on the middle right. And on the far right, you see a pebbling strategy for a larger network. So that's just for the eye candy. So let me just illustrate how the pebbling goes in this example by animating. So first it will pebble A, then B, then C. Now D gets pebbled, and then at this point we can pebble E and then F, and then unpebble the remaining, the intermediary nodes. And in the end, we're left with pebbles in E and F. Now, I did forget to say one important thing about this entire pebbling game, what the rule was. So the rule of adding or removing a pebble is that the pebble on all the children have to be pebbled. So you can only add a pebble if you have already pebbled the children. And you can only remove a pebble if the children are pebbled. So these are the rules. So that's like you can only use a register if you computed the inputs. Um, Now, here we found a strategy with 6 pebbles, but then the question is, what can we do better? Can we just use fewer registers, 5 pebbles? And so, all right, so we can encode this as a bounded model checking problem. And the encoding is fairly, let's say, simple. For bounded model checking, we have to give an initial and a final state, and then a transition relation, and these are given here. And there's a Python notebook where you can run this as an illustration. So that's available online. The last sample application is yet another very different. It comes from economics. And so Casey Mulligan at the University of Chicago, he uses Mathematica, Redlock, and Set3 to model economical arguments and then check, say, corner conditions in economics. So, so what these applications illustrate is essentially different uses of SMT solving. What you see on this slide is a set of Microsoft research tools developed over the years. And on the bottom, features we have added to Set3 to support these user scenarios of the tools. Okay, so now the second part of the talk will give an introduction to the integration of how SMT solving use theory solvers. So in a nutshell, SMT solvers check satisfiability of a formula, modulo T, and the solvers have specialized algorithms. So another view of it is that you can view a SMT solver as a combination of a set for case analysis and theory solving for checking what the theory knows. In this example, we have an arithmetical formula with conjunction of 3 parts. The first part is x greater than 0, and the other part is y equals x plus 1, and then there's a disjunction. Now, we will create an abstraction of this formula, so give name to each atomic formula and send it to a SAT solver. Now, the SAT solver can find an assignment, and one sample assignment will set P1 and P2 to true. They have to. But to satisfy the disjunction, you may satisfy it by setting P4 to true and P3 to false. The meaning of those that assignment can now be retrieved by following the definitions, and then the theory solver can give a verdict whether that assignment is feasible. Now, in this example, the assignment was infeasible, namely if y is less than 1, then the combination of that y is x plus 1 and x is greater than or equal to 0 is unsatisfiable. So that gives us a new lemma, a new combination of atomic formulas that are infeasible. And we call that a theory conflict, and you send that back to the SAT solver, and now the SAT solver can find a new assignment. So that's a high-level view of integrating theory solving with a SAT core. So I'll use that as a basis for, as a hint of how we integrate theory solvers. But what are the theory solvers? So one way of characterizing the theory solvers is that they fall into one of 5 categories listed here. At the base, the simplest theory solvers essentially compile into SAT, propositional SAT. So these are the finite domains. And then there's a small set of base theories from which other theories are essentially encoded into. And these base theories are arithmetic and uninterpreted functions. So other theories are essentially the reducible theories. They reduce to the base theories. That's the simple case. The not so simple case is when you have theories that mix, say, arithmetic with non-arithmetic reasoning. Um, and there's some examples of those theories. And then finally, there's a category of theories that I would call propagation rules. So the Boolean, here's three examples of finite domain theories, bit vectors. So when you reason about bits in bit vectors, um, we can treat a bit vector as a set of Boolean variables, and then just reason about those Booleans. And that's still the dominant method of solving bit vectors. In the middle, you see an at most and an at least constraint. And I'm using Python notation, the Python input notation that's Z3 accepts to illustrate these formulas. And these, so what these at most and at least formulas mean is that at most between P, Q, and R propositional variables, at most one of them can be true. So it's not possible to have P and Q true at the same time. That's what that constraint says. And you can encode such constraints into clauses. That's possible to compile them just like we compile bit vectors. But there's also specialized solvers for such inequalities. So these are called pseudo-Boolean constraints. In the base theories I mentioned were arithmetic and uninterpreted functions. On the top, you see one example of an arithmetic formula, and the bottom, an example of an uninterpreted function formula. So here you have a function symbol f, and the goal is to find a solution for f and x that satisfies the constraints. So for example, if we have f of x equals x and f triple of x equals x, then there is indeed a solution. And one possible solution is where the f is the identity function and x is some element. But if we add another constraint where f of x is different from x, so that will rule out f from being the identity function, then in fact this constraint is no longer satisfiable. So that's uninterpreted functions. Let me just go a bit more detail with the arithmetic solver. So solving arithmetical formulas is a big enterprise. So this is a schematic of the ingredients of arithmetical solving. So the SAT solver takes care of backtracking. The backtracking asserts bounds on variables. Then we solve, given bounds and variables, we solve constraints globally using simplex. If the constraints remain satisfiable, we can propagate bounds and inequalities. If the constraints remain satisfiable over the real still, we can see if there's a solution over integers for variables that must be of integer type. If those are solvable, then we solve for multiplications. So if the formula has nonlinear multiplications between variables, then linear programming is not enough. And there are different methods for solving those. So I'm going to zoom in on the bounds propagation to illustrate the global propagation. So for sake of argument of an example, we're given some formula where you have x plus 1, the SAT solver says, okay, I'm going to make a k-split, x plus 1 equals y, and y minus 1 equals z. And that gives rise to bounds propagation. And through bounds propagation, we can learn that x equals z. And then we can tell the other theories, okay, we have this new knowledge. We deduced x equals z, and now you can simplify formulas using those. And there's indeed a complete method for learning inequalities. And roughly speaking, it goes like as follows. You turn non-strict inequalities in constraints into strict equalities. And then you check whether the inequalities are still satisfiable. If they are not satisfiable, so they were satisfiable with these non-strict inequalities, but they become unsatisfiable. Then there's a minimal unsatisfiable core, and now all the inequalities in the unsatisfiable core have to be non-strict, so they have to actually be equalities. So that's a complete method, but I want to illustrate a faster but incomplete method that we developed. So it goes, it's easier to illustrate with a more full example. So for sake of argument, we have 4 variables, x, y, z, and u is fixed to be 1 using inequalities, and then the 3 inequalities asserted, x, y, and z. The solver actually doesn't see these inequalities. What it sees are global equalities with slack variables and then bounds on the slack variables. So that's what the solver sees. Furthermore, it will pivot, it will solve for the global equalities. And here I've pivoted, so x, y, and s3 are written as they're solved using the other variables. That's what pivoting will do. And so once you have pivoted variables, you can infer new bounds. So in particular, we can learn that S1, S2, and S3 all have upper bound 0. So now all of these variables, S1, S2, S3, are going to be fixed. And at this point, we can subtract the first 2 equalities. So x equals z minus u minus s1, and y equals z minus 1 plus s2, and we can infer that x equals y. Now, there's a subtle complexity involved with this procedure. If we were to subtract and add equalities like this, then that becomes quite expensive very quickly. So adding values with bound requires significant runtime. So one way of dealing with this is to notice that we already have values for all the variables from simplex. So the tableau, the state is feasible. We have some values, and then we can notice that 2 variables can only be equal, or 2 variables are equal provided they have the same value. If they have different values in the current evaluation, they will never be equal. But then the other condition is that they are connected through offset equality. So an example offset equality looks like this. So you have x is solved as y plus something else, but the something else is all fixed to a constant. So all the other variables, z1 and z2, are fixed. But this method never has to compute what is a1 times z1 plus a2 times z2. It never needs to compute this. It just chases these inequalities, and that's a significant time saving for the globally learning that x equals y. So in this example, if x equals 3, then y is 4, and z is 4, and y is 3. So let me press on with the other theories, the reducible theories. In this example, the theory of arrays is reducible to uninterpreted functions. And the reduction proceeds by essentially instantiating the theory axioms of arrays. So if you have a store symbol, then if you're reading back what you just stored in the array, so here we're storing y into the array A, and so if we read back at x, we're going to get what we just stored, so we're going to get y. So that's an instance of the theory of array. So we add that, and then the uninterpreted function reasoning doesn't know about arrays, but it deduces that there's an inconsistency in this example. So if I remove that disequality, the constraints are now satisfiable. And so this is a bigger, more complete variant of expanding the array axioms. So we still expanded that store of with the x equals y, but we got some other equalities that take care of extensionality. And then we can find a solution over uninterpreted functions for this expansion, and that gets converted back to a model for arrays. The hybrid case is when you have a non-disjoint combination of theories, and so reasoning about strings is one important example, where you can take lengths of strings, and the length is arithmetical. So in this example, there's a formula where you have s and u, and their length equals t, and s is a prefix of t, and u is a suffix of t, and then so in that case, t has to be the concatenation of s and u. So the last in the category of theories is the case where we have global propagation. So it's not always the case that we can express succinctly using the existing established say set of theories what we want. And in principle, this is open-ended. So what to do with what you cannot express succinctly in formulas. So if we were expressing this constraint in a formula, we would get hundreds of thousands of atomic formulas. So one atomic formula would be x0 plus x1 equals 42. And we would get, say, the cross product of all possible pairs of I and j for it. So that's not very satisfactory. That blows up the search space and bloats the solver. What we can do instead is to introduce code for such constraints. So a new feature is allowing such callbacks into SET3. I'm currently using this for production line optimization for a car manufacturer of electric cars in the US. So this is useful for these operations research scenarios. Okay, so we have reached the end of the road of the talk. So I've given two examples of one is global inferences, the equality propagation, small nugget in the arithmetic solver, and then a global propagation as now a programmable feature that's also relatively new. And in the proceedings, there's a further description of both of these parts. What I have not described in this talk is some of the common traits in many of the, or almost all of the theory solvers we have, is that they exploit a duality between finding models and finding proofs as SAT solvers, conflict-driven clause learning solving has done, but we do it at the SMT level. So there's another, say, angle perspective to solving that I haven't described. Of course, I hope this is my shameless plug to the conference the steering committee of the conferences to when the conference becomes physical, I will be very happy to come to Brazil and give tutorial and meet you. There's also another theme that I mentioned. I'm putting a new core in place for SET3, and it will have interpolants without proofs and generate proof objects, model theories, so that we can certify systematically what the solver does. and there's some other goodies. For example, from the applications of blockchain smart contract reasoning, is evidence that the current generation of bit vector reasoning is insufficient for reasoning about these large bit widths of smart contracts. So they use 258 bits. The SMT world needs to move beyond what we have done in the past 10 or so years with bit vectors. Okay, so that summarizes the talk. I hope there are some questions. I'll be very happy to discuss.
Okay, so thank you, Nikolai, for this great talk. I would say that's inspirational since you have illustrated an application of formal techniques on the development of non-trivial solutions. And I think that as a community, we are always seeking for these to develop ideas and techniques that can be used in projects for dealing with non-trivial problems. I would say that I have learned a lot by reading the paper and watching the presentation. So thank you once again. Uh, we have a first question by Rohit Gay. He says, I started using Z3 since
Uh,
20. Sorry?
I, I have a question related to the strategies used to guarantee sound validating it. What the main strategies used? PLDI 20. I'm not sure which PLDI 20. I guess it's fuzzing. Yeah, I see. So there, in recent years, there's a few groups that have started fuzzing SMT solvers. So they find a lot of bugs and corner cases, and I've been very busy patching. Um, okay, sick plan. Yeah, okay.
Yes.
Um, and so the fuzzers will find bugs, and often these are say in areas that users may find. In many other cases, it's by tweaking some configuration options that nobody use. Therefore, those bugs are say less relevant for users. But nevertheless, these all bugs are taken seriously. We can validate what the tools for finding bugs take advantage of is that we can validate models. So if we say that we have something that's a model, we can check whether it indeed is. Users can also do that indirectly by getting the model and then plugging, specializing the formula to make it simpler and see whether it still is true. And then otherwise, you can run different solvers and compare their outputs. What the validation, what the proof logging validation that I think SMT solvers should move to is a variant of the DROP and DRAT proof logging that has been very influential in SAT solving community. It essentially logs clauses that were learned, and it doesn't require big surgeries within the SAT solver. And indeed, the SAT3 SAT solver does generate DRAT proofs. And so the road ahead for the SMT world is to learn from this, to have simple proof logging and powerful checking for this. So I'm actually soliciting whether someone is interested to write a proof checker independent of SAT3. I already have a proof checker within SAT3, so it basically assumes say some internal soundness. Okay, so next question. My question, does SAT3 use an off-the-shelf SAT solver? It uses its own SAT solver. And I've added all the all the latest tricks, or most of the latest tricks. So the main, the best SAT solver out um, around these days is called Cadical by Armin Bier, and so SAT3's own SAT solver does not compare at the level of Cadical, but it does integrate the main heuristics and in-processing techniques. Let's see, so maybe there was some other question. C3 would like an answer to this question live. Okay, yes, just say.
There is another question in the chat by Rodrigo Pereira. And Leopold is also asking us to read the questions aloud because when someone sends a question using the Q&A window, it's not available for everyone.
I don't see the. Can you read it?
Yes, sure. What were the biggest challenges you had to overcome during the initial development of Z3?
Actually embarrassing. So I didn't give the story of Z3. And I sort of assume that the audience is somewhat aware of it. So Z3 was developed starting 2006 with Leonardo de Moura, who's Brazilian, and he also gave a talk at the conference 10 years ago or so. And I think it was essentially our first system paper on Z3 as part of. So the initial challenges was well, I would phrase it as follows: the initial opportunities were that there was a good set of use cases within our research group. And these were symbolic execution and then program verification. So we developed engines for quantifying instantiation, so equality matching, and then solving. So some of the challenges over time, so the 2020 hindsight is always the easiest. So I think the challenge with writing an SMT solver is the deep complexity of dependencies. So a lot of things depend on each other. And what I'm seeing today is that the core that was put in place several years, a decade ago, more ago, is needs to be modularized better, such that we can extend it for more powerful in-processing. So I'm not able to do in-processing at this point with what we have. Oh, I see, 2009. Oh, I thought it was before, but okay.
I have a question myself. So by modernizing Z3 with these new ideas, can you foresee applications in the context of Microsoft products and solutions that you will be able to tackle now that was not able to tackle before?
Well, so I actually gave an example with a user propagator.
Yeah.
And that was directly driven by one application. So I'm currently developing a production plant configuration for a car manufacturer, and they essentially solve a multi-knapsack constraint. And in the operations research community, there are ways of doing global constraint that well, typically would involve some language constructs. And what I think is the opportunity here is to introduce the programmability, so we can encode the global constraints using a program. So that makes it flexible. And so if I were to encode those constraints that, and I gave a schematic, like a simplified example of what I'm seeing in the application, it leads to incredible space blow up. And with the encoding, I can solve the problems in a few minutes. So it goes from infeasible to fairly easy. But it's open-ended. So that was just one example of. And what I'm seeing with the okay, so why move to a new core is that, well, now we pay a price for theory solvers that we don't use because we load them all up front. The bit vector reasoning is still bit blasting, and it needs to be incremental, so avoid bit blasting. And yeah, so there are many such examples.
Okay, thank you. We still have time for maybe 1-2 questions. Well, maybe to give time to someone type the question, I would like to ask a final one, at least from my side. So it's quite clear for me that Z3 is a kind of a foundation software for many other Microsoft products. But besides Z3, what are the other, let's say, main tools that the formal methods research team at Microsoft is working now?
So Leonardo de Moura has been working on the lean system since 2013, and it's quite widely used around mathematics and compilation of functional programming. And then there's fuzzing. So Patrice Godefroy, who developed Sage, has broadened out to develop REST fuzzing tools. So for web services, and those were made open source last week, as a matter of fact. So I recommend taking a look at those. So those don't use SMT solving, but they use model-based fuzzing. So I think that's an exciting, say, development from formal methods point of view in our group. Now we have, there are many other developments around, say, compiling for machine learning and then code synthesis from also the CPT-3.2 models and so on. Yeah, so SMT is we have quite a number of applications or developments around, besides symbolic solving. But then on the other hand, there's often some small ingredient where you want a small formula that wants to come out of the program, and for that purpose we have the SMT angle.
Okay, thank you. So let me just check whether we have some questions in the Slack channel. No. So if we don't have any other questions, I would like to thank you very much, Nikolai, once again for your talk and for joining us. A round of virtual applauses for you. And I think that this ends this keynote session. Thank you very much.
Thank you very much again for inviting me.
Bye-bye.
Bye.